Let's do it. Okay. So we move on to section 11.6, which is talking about absolute convergence and the ratio and root tests. Okay, so I have a couple definitions up here and I have a theorem up here. Okay, so when we're talking about absolute value, right? That just I'm taking, a term and I'm applying just making it positive, right? So if it has any negative signs on it, it just becomes a positive thing. So when we're talking about absolute convergence, right? If I had my series AN equals 1 to infinity, right? It's not just looking at that series now, but instead I'm going to look at its absolute value. Now, in some cases, that might not matter because it might have already been positive, right? But especially in the case of alternating series, it's going to take off the -1, right? So our first definition here is that a series is called absolutely convergent if the series of absolute values, sum of the absolute value of the AN term, is convergent. Okay, so no matter what the series is, if I can take the absolute value of each term and add together, and it converges, it gives me value, then I can call that series absolutely convergent. Okay, so one example for us, get us started here, is if I look at the series -1 to the n minus 1 over n squared. Okay, now question is, right, how does the convergence of this thing work, right? Well, we have the alternating series test to work with this one, right? But also I can just I'm going to take the absolute value of each term, right? So if I take the absolute value of each term here, which would be -1 to the n minus 1 over n squared, what would that give me? Right? Same thing happen to the n squared. Is n squared positive or negative? It's always positive. Okay. Let's get away, guys. Come on. We're so close to the end. Just bear with me, all right? I know it's a lot. This is always positive, so that doesn't matter. If I have -1 to the n minus 1, that means anytime I have a -1, that means it's going to go away. So that whole term doesn't matter. So the absolute value of this thing is simply just going to be 1 over n squared, right? So if I want to look at the series, the absolute value of this series, I'm simply looking at the series n equals 1 to infinity of 1 over n squared. Okay. Now, tell me about this series. Is it convergent or divergent? Okay, how? It's not the harmonic series. 1 over n is the harmonic series, and that one actually diverges. So that's not the test. That's not what we'd use here. What test should I use to say this? Not power series. We haven't even talked about power series yet. That'll be next week. So do I have anything on the top? It's just 1, right? Okay, and the denominator I have n squared. Okay, so I have n to a power, right? Into the p series, right? Is p greater than 1? Yes, p is greater than 1. Okay, so since it's greater than 1, we have 2. Does that mean my series converges or diverges? It converges. Good. So this is a convergent series, right? But this was the absolute value of this series, essentially, kind of the absolute value of each term, right? So that means that this series that I started off with, this n equals 1 to infinity of -1 to the n minus 1 over n squared. This is a absolutely convergent series because take the absolute value of each term, it's still convergent. Okay, so it's an absolutely convergent series. Make sense? Is that good? Okay, great. Now, let's, instead of looking at this example now, let us go to the example of if instead of n squared, I have n. Right? Now, we might have something to say about this series in particular. Well, actually, how would I find if this series is converging or diverging typically? Right? What would I do? Yeah, use the alternating series test, right? So it has to pass two conditions, right? The first condition is that the limit as n approaches infinity of b of n, which in this case is 1 over n, has to be 0. Is that true? Okay. And then it also has to pass that b of n plus 1, 1 over n plus 1, is less than or equal to 1 over n. Is that true? Okay, good. For all of our natural numbers, it's definitely going to be true. Okay, so does this converge or diverge by the alternating series test? Converges. Okay, good. However, let's take the absolute value of all the terms. So I'm going to take the absolute value of -1 to the n minus 1 over n. So what is each term going to look like in this case? I take the absolute value of it. Okay. Yeah, n's going to stay the same, right? Because the positive value of n for 1, 2, 3, 4, 5, 6 is just n. And then what's the absolute value of -1 to the n minus 1? It's just 1, right? You either get -1 or 1, so if I take the absolute value, it's always going to be 1. Okay, now, is this series convergent or divergent? This one's not convergent. Okay. It has the power of 1 on it, which by p series, when p is equal to 1, it diverges. Okay. The harmonic series diverges. Okay, so this is this one diverges. Okay, so we have, if it has a -1 to the n minus 1 on it, then it converges, but if it doesn't have a -1 to the n minus 1 on it, then it diverges. Okay, and we call this type of series conditionally convergent. So conditionally convergent means that it's convergent, but it's not absolutely convergent. It's convergent with the -1 on it, but it's divergent. Right? Make sense? Good. So that is our notion between the kind of our two different ideas there. Okay. So we have a nice little theorem here. That's going to go after this. So we have absolutely convergent, conditionally convergent. Now, if I have a series that is absolutely convergent, right, then that means that same series is definitely going to be convergent. Like it's guaranteed. It's, if it's absolutely convergent, then that just dominates, right? Then it's convergent. It's not going to somehow end up being divergent, right? So maybe a practical application of this theorem is to take an example like the book is. I'll change it up slightly. So we're going to have the sum from n equals 1 to infinity of sine of n over n squared. Okay. So I want to determine if this series is convergent or divergent. Let's say. So this is an example here. Okay, I want to determine if the series is convergent or divergent, right? So there's going to be signs fluctuating here, so it might be a little odd. And the example we did yesterday had a pi in there, so it was definitely just -1, 1, -1, or 1. But there's no pi in here, so it's just sine. It's just sine of n, right? So if I put 1 in there, I get sine of 1, which is, somewhere. It's somewhere between 0 and 1 potentially, but it's definitely not 0 or 1. It's some weird point in the middle. So this might be a little hard to work with. So what we might do instead is I might look at the absolute value of the series. Okay, so I'm going to take the absolute value of it. Okay, now n squared. What is the absolute value of n squared? What is it? It's n squared. Okay. Now, the absolute value of sine n depends. So I'm gonna leave that, but it's the same thing as absolute value of sine n over n squared. Okay. Now, instead of looking at this series that we started off with, we're gonna look at its absolute value version, okay? Can I take this series and compare it to something in some way, or is there another sort of test that I can use? The test for divergence might be a little hard here. Just getting the sign. It's probably a little hard to tell what the sign would be. What do we think? What ideas do we have to? Right, so I want to find the convergence of this series. Can I say anything about this series at all? What do we think? Good. I can compare this to 1 over n squared because the absolute value of sine of n is always less than or equal to 1, right? And since it's absolute value, I don't have to worry about negative signs. I only go to 0, right? So this is definitely, in all cases, less than or equal to 1 over n squared. Okay. We talked about this series already. Is it convergent or divergent? Okay. It's convergent. By what test? By p-series. Okay, we have to use p-series to do that. Okay. You could use integral test, I guess, but why not just use generalization? So what does that tell me about this series? This one's also convergent by what? Why is it convergent? By comparison test. By just our basic comparison test too. Okay, good. Now, if this one's convergent, if the absolute value of the series is convergent, right? We can say, use the theorem to say that this guy is convergent by, and it's probably a little weird stuff. Sounds a little weird, but I'll say convergent by absolute convergence. Right? Since this series, the absolute value of the series is convergent, it's absolutely convergent, and that just means the series itself also has to be convergent. Okay? Right, because you might have some negative terms in here, but this is all positive, so it's definitely going to be smaller. And so this one's small enough, now it should certainly be small. Okay. Questions? Anything, please ask me if it doesn't make sense. Okay. Cool. So that might be useful, right? If I'm dealing with a problem and I want to know if it's convergent, maybe I can look at it, see if it's absolutely convergent in some way, right? Now, is it okay if I erase this over here? I still need it. Okay. Now, what we're going to be learning today in terms of our tests are going to be a couple of ways in which I can basically take a series and just determine absolute convergence just straight from these two tests. Okay, so it kind of, instead of like having to do that extra layer in the middle and create the other series, I can just take the series as it is, and if it works a certain way, then it's going to absolutely converge. Okay, and so one of the tests that we're going to do today is called ratio test. Okay, ratio test. What does the ratio test say? It says, has 3 parts to it. First part, if the limit as n approaches infinity of A of n plus one over A of n equals L, which is less than one, then the series sum from n equals 1 to infinity of an is absolutely convergent. Okay, so if I take the n plus one term over the n term and I compare the ratio, take the limit of the ratio, and it gives me a number which is less than one, the absolute value, which is less than one, then the series is going to be absolutely convergent right off the bat, that we can guarantee, that we know. We want this ratio to be at a small enough level to know there's going to be a consistent decrease. There's not, none of the values are going to be close enough to where it doesn't really go down as far as you need it to. It's like it always decreases. Okay. Now, for the second part, if the limit as n approaches infinity of that same quantity, a plus 1 over an, which equals L is greater than 1, or the limit as n approaches infinity of an plus 1 over an equals infinity, then the series sum from n equals 1 to infinity of an is divergent. Okay, here's the second part. So let's think about this one, right? So if the ratio of my terms as they go along, it ends up being greater than 1, that means I keep adding more each time, right? Or obviously, if it's infinity, that means the next term is getting way bigger than the term before it. So what these mean, if I have either of these cases, then that series has to be divergent. There's no other way around it. Okay? You just can be guaranteed that if you get like 2, 3, 4, 5, 3 halves, 4/3, whatever, or if you get infinity, then the series is going to be divergent. Okay? Finally, so talk about two cases so far when L is less than 1, when L is greater than 1 or infinity. There's one that's missing. What case is that? None of it's 0. 0 is included here. I feel like somebody said 1. If it's equal to, yeah, if the limit as n approaches infinity of an plus 1 over an equals 1. Okay. The ratio test is inconclusive. Okay. So what does that mean? Well, that means that if I get a limit and it's equal to 1, then the ratio test can't tell you. You're going to have to use something else. Okay, you're going to have to find some other way to determine whether the series is convergent or never. Okay. Now the ratio test generally can be like a pretty nice one to use. Comes in pretty handy. Generally, you can pretty easily tell. Oh yeah, this will, this is going to give you the right thing. If I have these two cases, it's pretty easy to determine. But there's some cases where you get convergent, absolutely convergent, or even conditionally, or maybe even divergent ones where the ratio test is going to be right. Like if I took 1 over n squared, this would happen, but we know that one's absolutely convergent. If you have 1 over n, that would give you 1, but that one is conditionally, right? And then if I took like 1 over the square root of it, it would give me 1, but that one's divergent. So, yes.
This tells you it's absolutely convergent.
Yes.
So if you get
Yes. Yep, it could be conditional. But you have to check it otherwise. The test will not tell you if something's conditionally convergent or not bad. You have to test it yourself. You have to do something else to it. Okay. Any questions on the definition at this point? There's a proof in the book if you're interested. I can't really do the proofs at this point just because they don't really use any like elementary ideas or stuff that you would cover in this class as in depth. So I'll be skipping over that, but believe this is true. I mean it does make sense on a logical scale, right? You want your terms, the ratio of your terms to go down. You don't want it to go up, right? If it goes up, it's a problem. And if they kind of get around the same, it just kind of depends on where they end up at. Okay. Good. So let's go ahead and do some examples. Right? Who write those examples? I don't know. Could be wrong, yes. Maybe we'll just spend the rest of the class time proving that we don't even do it. Okay. Let's see. So let's do, so this is going to be problem number 8 in the book, which says to use the ratio test to determine whether the series is convergent or divergent. Okay, so we are given sum from n equals 1 up to infinity of -2 to the n over n squared. Okay, so I want to take this series and I want to determine whether it's convergent or divergent. Okay, so to do that, right, notice we always start with the same. We're always going to start with the same thing, which is this limit is n approaches infinity of an plus 1 over an. Right? So I'm going to write that limit is n approaches infinity of the absolute value of an plus 1 over an. Okay, and this is going to be equal to limit is n approaches infinity of the absolute value. Okay, now. If this is n plus 1, where do I put that? Where do I put n plus 1 at? Where's the n plus 1 going to go? I go wherever we're looking at. Everywhere where there's an n, right? So we're going to have -2 to the n plus 1 over n plus 1 squared over, and then we're going to have an, which is just whatever the term is on the inside. So it's going to be -2 to the n power over n squared. Okay. Question. Why do you think that absolute value is important? What is it going to do to our problem? How's it going to change the inside? What is it? I think you're no negative signs. Yeah, all the negative signs are going to go away. So I'm just going to put 2 to the n plus 1 and 2 to the n plus 2. So I'm going to have the limit as n approaches infinity. So for the top, for example, I'm just going to get 2 to the n plus 1 over n plus 1 squared. Now, when it comes to the denominator, right, if I divide by a fraction, I flip it, and then I multiply it instead. So I'm going to multiply by n squared over 2 to the n power. Okay, good. Now, let's see if anything's, is there anything that's going to cancel here that I could kind of like cancel out at the moment, make this a little simpler? What do we think? See anything? Yeah. So I'm going to rewrite this. This 2 right here, the 2 to the n plus 1 is 2 to the n times 2 times n squared over n plus 1 squared times 2 to the n, right? Now notice we have 2 to the n, we have 2 to the n. So those are going to cancel with each other, right? So I'm left with the limit as n approaches infinity of 2 times n squared over n plus 1 squared. Okay, now you can feel free to follow this if you want to. It'd be n squared plus 2n plus 1. But we can find this limit at this point, right? So again, we go right that below. It's the same thing as n squared plus 2n plus 1. what is the limit of that thing going to be as n approaches infinity? If I have 2n squared over n squared plus 2n plus 1, it's going to be 2, right? It's the same, they're the same power, so I can just take the ratio of the leading terms, the n squared, so I take 2 over 1, which just gives me 2. Okay. Is 2 greater than, less than, or equal to 1? It's greater than 1. Okay, so what does that tell me about my series? That it diverges. That's it. Okay, so the divergence. Yes. We don't, and when we talk about divergent, we just mean like, yeah, I guess absolutely divergent. It just means it doesn't converge. It wouldn't converge if the -1 was there, and it doesn't converge if the -1 wasn't there. It just fails both. Yeah, it just fails both cases. So yeah, absolute divergence. We just don't typically use absolute divergence. You could technically like exchange the definition. You could be like, say this one's convergent, and then say this, say convergent, and then be like, you know, conditionally divergent, and then you'd have absolute divergence. But this is probably the more more straightforward way to kind of the glass half full versus empty look at it. So, any questions on that one? Okay, let's do another example. That'll be number 10. Let's hop on to the next one here. Number 10, we're going to have a sum from n equals 0 to infinity of -3 to the n power over 2n plus 1 factorial. Okay. So, as you might guess, I'm going to set this up the same exact way. We're going to take limit as n approaches infinity of absolute value of n plus 1 over a n. And give me the limit as n approaches infinity of. Now, what do I get when I put n plus 1 in here, right? I'm going to get -3 to the n plus 1. What's going to be inside that factorial here? Right? If I put n plus 1 in there, do I get 2n plus 2? Do I get, like, what's going to happen, right? We have to take 2 times n plus 1 plus 1. So it ends up being 2n plus 3, because I have to take 2 times n, I have to take 2 times 2, right? And then plus 1 over, and then just -3 to the n over 2n plus 1. Okay. Now, okay, what's that absolute value going to do? Get rid of the negative signs. So we're going to have 3 to the n plus 1 over, and I'm going to write this as, so we have 2 times n plus 2 times 2, or 2 times 1, which is 2, and then plus 1, so we get 2n plus 3 factorial times 2n plus 1 factorial over 3 to the n. Okay. Now, we have to be a little wary here, right? We're dealing with something a little bit new. We're dealing with a factorial now, right? So we need to kind of walk through this, right? Remember, so if I give you n factorial, right? Or let me do a specific example first. If I give you 4 factorial, you would tell me that's what?
1 times 2 times 3 times 4.
Good. I would go the other direction, but yeah, 4 times 3 times 2 times 1. Just it's a little bit easier to kind of put it like to go through it that way. So 4 times 3 times 2 times 1, right? Similarly, for n factorial in general, this is the same thing as n times, and I go to 1 below n minus 1. and then I would go to one below that, and minus two, and one below that, and minus three, all the way down until I get to times two times one. Okay? But it may not be the most convenient way for me to write this, right? To write all this out. If I'm just wanting to cancel parts out. So let's look at this a little more. If I have 4 times 3 times 2 times 1, right? What is 3 times 2 times 1? What is it? Well, the number is 6. It's 3 factorial. That's what I was looking for. This is 3 factorial. So I get 4 times 3 factorial, right? Similarly, for this guy, if I ignore the n for now, and I have n minus 1, n minus 2 all the way down, that's this is going to be n times n minus 1 factorial, right? So I can rewrite a factorial by just taking out, a couple terms and then just writing factorial that includes everything that's left. So what way that we're going to apply this here, right, is that 2n plus 3 is a bigger number than 2n plus 1, right? How many terms do I need to take out to get to 2n plus 1? You need to take out 2 of them. So I'm going to write this as the limit as n approaches infinity. Again, we have the 3n plus 1, so I'm going to write that as 3 to the n times 3. I'm going to write 2n plus 3 factorial as 2n plus 3 times 2n plus 2, right? You subtract 1 each time. And then that's going to be times 2n plus 1 factorial. Right? Everybody see that? Makes sense? Right? I just take 2 terms out, and then I want to get to that 2n plus 1 factorial. Okay. And this is going to be multiplied by 2n plus 1 factorial over 3 to the n power. Okay. What's going to cancel? That 3 to the n is going to cancel. What else? 2 to the n plus 1 factorial is going to cancel out. So I'm going to be left with the limit as n approaches infinity of 3 over 2n plus 3 times 2n plus 2. Everybody tell me what that limit's going to be? 0. Right? Because I just have a number over something that's going to go towards infinity, right? So we just get 0 back here. Good. So, is that bigger than, smaller than, or equal to 1? Definitely less than 1, right? So, what does that tell me about my series? What is it? It's, yeah, absolutely convergent. In fact, this one's very absolutely convergent because it goes to 0, right? That just means that the top, that negative 3 to the n had nothing on the 2n plus 1 factorial. It like couldn't stop it. So yeah.
Where did that other 3 come from when you wrote the limit? Yeah, that one.
We had 3 to the n plus 1, right? Which is the same thing as 3 to the n times 3 to the 1. Yeah, so this is 3 to the 1 technically, but that's what we're going to do. Any other questions? We're in here. Okay. Let's do one more. This one's gonna be a little interesting. I'm gonna leave that up. So I've got grace. Okay, so we're gonna have the sum from actually this is 18. So it'll look funny, but when I do that, I'll just do it 1 with 8 there. So we're gonna sum from n equals 1 to infinity of n to the n power over n factorial. N factorial over it. I want to determine if this is absolutely convergent, conditionally convergent, or divergent. Okay? Which this section says to use ratio tests, you would expect it to be one of the first two instead of the third one, but. Okay, so I have n factorial over n to the n power, right? So, what's my first step if I'm doing ratio test? Right, what we want to do, we need to use, we want to plug into this limit, right? That's how we use ratio test. Ratio test is I have to use that limit. So I'm going to take the limit as n approaches infinity of a n plus 1 over a n, which is equal to the limit as n approaches infinity of, I'll have absolute value of n plus 1 factorial over n plus 1 to the n plus 1 over n factorial over n to the n. Okay, good. Now, the absolute value really doesn't affect anything here because it's already positive. So I can just, I'm going to rewrite this as the limit as n approaches infinity of, so we're going to have n plus 1 factorial over n plus 1 to the n plus 1 times n to the n over n factorial. Okay, so we have to figure out how we're going to evaluate this. So what ideas do we have? Maybe for simplifying or canceling. What we want to do.
Break down the n plus 1 factorial.
Okay, good. So I'm gonna, how should I break it down? How should I rewrite it? N plus 1 times n factorial. Okay. And then we're gonna that multiply by n to the n. Now, it doesn't seem like it might help at the moment. Well, actually, it might help us a little bit. I might go ahead, I have n plus 1 as the power here. So maybe we can just go ahead and rewrite that. So I'm gonna have n plus 1 to the n times n plus 1 times. Okay. Is anything gonna cancel?
Oh, the n.
The n factorial will cancel. Anything else? N plus 1, right? So we're going to be left with the limit as n approaches infinity of n to the n over n plus 1. Okay. Just tell me what the limit is, right? You guys know. Stay, come on. Just kidding. This one's a little tricky, but yeah.
You want to rewrite it as 1 over x to the n, one more.
No, because it won't. It's not the same thing as 1 over n to the n, right? You would, because I'm not. It's not 1 to the. It's not. I have n to the n plus whatever down here. So it'd be more like 1 plus something. It's. I can't just like cancel that easy, right? This term's bigger, right? But it's not that much bigger. It's not gonna look like it again. So I can't really cancel like that. Okay, how we're gonna do this, right? Is maybe I'll bring my work down here. They both are to the n power, right?
You take the n.
Not in this case. We have tests where you can take the nth root, but we can't just take it here, just because n is involved in the limit, so it would kind of mess up the value. Okay, so we have the limit, as n approaches infinity, we're going to have n over n plus 1 to the n power. Okay? Right, because they're just both to the n, so I can go ahead and do that. Now, I wanted to do this one because I figured it'd be fun, but also there actually is a limit we recognize that's hidden here somewhere. We just have to play around with this a little bit. So what I'm going to do is I'm going to take the inside and I'm going to I'm gonna flip it. Okay, so if you remember when we did like L'Hopital's rule and stuff, we would say 1 over the reciprocal, and so I'm gonna do that here, right? Now, if I take 1 to the n power, what's that gonna be? 1. So we get the limit as n approaches infinity of 1 over. Now I have n plus 1 over n. Can I divide that n from the terms here? So I'm gonna get 1 plus 1 over n, and then to the n power. Now remember, with limits, we can take the limit of the top and bottom, right? And the limit of the top is going to be 1. We actually know the limit of the bottom. This is one we should be familiar with. I think I showed this one class a few weeks ago. So this is E. This is the definition of E. So we get 1 over E. So might be something to remember to keep track of. But yeah, that is the definition of E. Okay. And if you weren't sure about that, you could also like use techniques we did like with L'Hopital's rule to find the limit of that thing and show that it's E just the bottom, but this isn't E, so we get 1 over E. Okay. Now, how is 1 over E related to 1? Is it bigger, smaller, equal? Smaller. So it's less than 1, right? So what does that tell me about my series? Convergent or divergent? Convergent, absolutely convergent in this case. Yeah. Absolutely convergent. Questions, comments, concerns, anything for me at all? Yeah, that's a fun one. That one's definitely absolutely convergent. It depends on the class, but sometimes they kind of teach a hierarchical sort of list of functions, so you can know whether it converges and diverges just by what you have. Like, I can kind of sketch it out. We have some time here, but if you have, right, you have this kind of list of different functions, depending on what the ratio is that you take of them, you can tell if it's going to be convergent or divergent. If I have a natural log of n over some like nice power p like 2, 3, 4, 5, then it's definitely going to converge. And if I take the ratio of these two, it converges, but both the opposite way, it diverges. Just because each time you're growing a lot faster than the functions do, but I don't expect you to like remember that. It would apply here as well, because you have n factorial over into the n, but into the n is way faster. If you don't believe me, just take a couple numbers and like do a few examples and see how fast into the n explodes. I will probably try to write them out. I'll try maybe like a shortened version of each one on the formula sheet. So like, obviously I want you guys to know how to use them, but if you forget the exact details, then you can reference it. So I plan to have some for you to have. I don't know, that formula sheet probably a little bit more complicated, right? But I'll get it. Okay. Questions? Anything else for now? Before I move on to root test. I think that is no. Okay. Good. Book actually does when I wrote into the end of root factorial, the book actually does that one of the examples, and you get the result instead of being 1 over E ends up being, I think it just ends up being E, which is greater than 1 in that case, so you would say divergent. But very basically the same sort of example or same sort of work. Okay. So root test also has three parts. Though it's used a lot less often because the cases where you use it don't happen as frequently, but still want to mention everything here. So we have the first one, which is that if the limit as n approaches infinity of the nth root of the absolute value of an L less than 1, then the series an is absolutely convergent. Good. So how the root test is starting out now, it says is instead of taking the ratio of terms, I'm just taking the root of my term, right? So if I take the nth root of the term and I take the limit of it, and it's less than 1, then the series is going to be absolutely convergent. Now, for some people, you might think this is the easier route to go, but if you just try to use this on any sum, it's probably going to make the limit harder to find. So would not be the most advantageous route in some cases. But if you have something particular set up, then you can totally use it there. Okay. For 2, we have if limit n approaches infinity of the nth root an equals L is greater than 1, or limit n approaches infinity. Oh, and this is absolute value. So that absolute value part is important, right? That's why. But absolute equals infinity, then the series is divergent. Then 3, if limit then approaches infinity of the nth root of the absolute value of an equals 1, root test is. Okay, so it's not very similar to the ratio test. Aside from how you started is different, but the same conclusions apply really. Instead of taking a ratio, we just take the root. So, yeah. One thing to mention about this test, where we just do some examples. There's not proof of this in the book, and obviously I wouldn't be able to do it anyway. But I mean, this is pretty straightforward, right? You just take the input and see what it is. One thing to mention is that if you do ratio test and you get the case 3 on the ratio test where it's equal to 1, don't try to do root test, because root test will not tell you anything different. It would also be 1 in that case. Because if it's 1 in one case, it's going to be 1 in the other, right? So whenever you're doing, like we'll talk about in the next section when you decide the order to do things, you don't want to do ratio test and then do root test. You kind of choose one or the other. Because if you've chosen 1 and it gave you 1 as the result, then you just have to stop. You don't do root test, right? You only go between the two, right? One's going to be easier than the other, right? So I'll show a couple examples where it's definitely easier to do the root test than it is the ratio test. But you can't. They're not like really sequential. It's just whatever is the one you cut. So we're gonna use root test here. So let's do a couple of examples. Okay, good. So number 26, we are going to have a sum from n equals 1 to infinity of -2 to the n over n to the n power. Okay, now this one's fairly obvious to see that they both have an n on it. So maybe it would be a good idea that n power on it. So maybe it would be a good idea for me to use root test to see what's going to happen here, right? So I'm going to, right? We want to take the limit as n approaches infinity of the nth root of the absolute value of a n, which is going to be the limit as n approaches infinity of the nth root of. Now, what is that absolute value going to do for my term on the inside? What's going to happen? Yeah, it's just going to make it positive. So I just get the positive. So I get positive to the n or n to the n. All right. So what happens when I take the nth root? Yeah, you just lose the n power of both. So I get the limit as n approaches infinity of 2 over n. Okay? Now what is the limit as n approaches infinity of 2 over n? 0, which is greater than, less than, equal to 1? Less than 1. So what does that tell me about my series? Absolutely convergent. Make sense? Am I good? Again, pretty straightforward, hopefully. This one's arguably easier to use because of, as long as you're using the case where it works, it makes sense, right? Yeah. Okay. Next, we'll do number 30, which is going to be about 30, which is going to be the sum from n equals 0 to infinity of the arctangent of n raised to the n power. Okay. So you would see a problem like this and see, oh, there's an n on it. Might be wise to use root test here, right? Take off that n power on there. So I'm going to take the limit, then approaches infinity of nth root of the absolute value of a n, which in this case is always positive in terms of my numbers, right? If I plug in 0, 1, 2, 3, 4, it's going to be positive or 0. So I'm going to have the limit then approaches infinity of the nth root of arctan of n. Okay. Now, what's going to happen here? I take the nth root. So we just get arctan. So we get the limit as n approaches infinity of arctan of n. Anybody want to enlighten us? Remembers what the limit as n approaches infinity of arctan is? It's not infinity, actually. So remember, arctan is tan inverse, right? And whenever we're talking about tan inverse, right? What is it? The domain does. So the domain goes from negative infinity to positive infinity. I can plug in whatever I want, right? Because tangent takes any of the value, typically, right? Tan, like, it can pop out any of those, right? Because my ratio between sine and cosine can be any number between negative and infinity. But the range of tan inverse, we only take a select few numbers. And those two numbers that we take are, or the ends we take is negative pi over 2, pi over 2, right? And it's at these two values where I'm going to have, I get infinity to get pi over 2, I take tan inverse of infinity essentially, right? Because that pi over 2 there's an asymptote for tangent. Because tangent sine over cosine, and cosine is 0 at pi over 2, so it's undefined at pi over 2. So we would say it's infinity in that case. And the range, and then by negative pi over 2 get negative, right? So in this case, I'm taking the limit as n approaches infinity of arctan of n. So I'm going towards that right asymptote on the graph. That right, or the horizontal asymptote, I guess, which is going to be 5. Okay, that's its stopping point. That's the highest value it'll get. Okay. Now, is pi over 2 greater than, less than, equal to 1? greater than 1. Right, because 3.14 is bigger than 2. So, what does that tell me about my series? Divergent. Just a couple examples of routines. Okay. Any questions for me on that? At all? Yeah. No, because so the tangent's periodic, our tangent's not periodic. Because in order for our tangent to be a function, you have to take off every other piece of tangent. So it isn't periodic in that case. It can't round up. Okay. So that should be good there. I might just mention a couple last things here. Most of the examples should be pretty straightforward. Let me talk about an example again of where you might have to deal with this third case, right? If I'm dealing with the sum as n equals 1 goes to infinity, right? 1 over n plus 1, right? Now, obviously, you might think of other ways to do this first. That would be easier, but let's just say that you went to this and you try to do ratio test on it. So if I did ratio test on this, I would get, so I would take the limit, then approaches infinity of a n plus 1 over a n, which is going to be limit is then approaches infinity of, and we get 1 over n plus 1 plus 1, n plus 2 over 1 over n plus 1, which is going to be the limit, and then approaches infinity of n plus 1 over n plus 2. Plus the limit is n approaches infinity of n plus 1 over n plus 2. 1, right? So here's an example of a case where you get the limit to be 1, right? This is a function, right? Now that doesn't, obviously that means it's inconclusive, so I can't say if it's convergent or divergent, so I have to use another test, right? The easiest test in this case to use would be to try to go for something like the limit comparison test, right? Just if I take off the 1 on the bottom, I get 1 over n, right? And that's divergent. You take that, do the limit. So if I compare this to 1 over n, right? And use the limit comparison test, I would get the limit as n approaches infinity of 1 over n plus 1 over 1 over n, which would be the limit as n approaches infinity of n over n plus 1. Which again, this is just like this one. It didn't really change much. So this is 1. So that's actually good in this case, because that means it's finite, it's greater than 0. So that means that if this one's divergent, then this one's divergent, right? Is 1 over n divergent? Good, yeah, it's divergent, so that would mean that this one's divergent. Okay, so we couldn't tell anything from ratio test, but you have other ways to do it. Okay, so if you encounter that here, that's what you would have to do. Okay, also, if I had n over n plus 1 raised to the n power, right? Your instinct might be to try to use root test on this because both things are to the n power, right? So then I would, when I did the root test, I take the limit as n approaches infinity of the nth root of n over n plus 1 raised to the n. So I would just get the limit as n approaches infinity of n over n plus 1, which is what? We did that one right over there. What is it? Oh, well, this is just n over n plus 1, right? Not to the n. I'm not taking the thing with the n on it. It would be, it's just n over n plus 1. So it's 1. The n's cancel out here, right? So in this case, it'd be inconclusive, so I'd have to find some other way to do that. Okay? So if you encounter a problem like that, right? If you're working it, you try to do ratio root and you get 1, you have to try it. But it's the same process. You just might have to abandon that one and go for something that you can sure hopefully find something. Okay. finally, the last thing, is I mentioned yesterday, this whole idea of, being like, I think I mentioned yesterday a little bit about taking the -1, if we take the sum of -1 to the n-1 over n, right? We just talked about earlier today that this is what type of series is this? Or we said this was? What is it? Well, it's an alternating series in terms of its convergence. Is it absolutely convergent? Is it divergent? It's conditionally convergent, right? Because it wouldn't converge if the -1 wasn't there, but it does converge if the -1 was there, right? Now, the reason why that's important to recognize is because oftentimes some people just, might just look at that and be like, well, it's convergent still. Why do I have to call it distinction? Well, I mentioned yesterday, the sum of this is, if you just take it at face value, is going to be the natural log of 2, right? But if you decide to change around the terms a little bit, right? So, for example, what the book does is it would be 1 minus 1/2 plus 1/4 minus 1 plus 1/3 minus 1/4 plus 1/5 minus 1/6 dot dot dot. Right? So this is supposed to be natural log of 2. And if I were to take this whole thing and multiply it by 1/2, right? I would get 1/2 natural log of 2. Right? So I would end up getting, I get 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12 dot 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 dot, and that should just be 1/2 that sum, right? Because if the sum itself is equal to the natural log of 2, taking half of it, taking half of each term should give me half of the natural log of 2, right? However, notice, right, that if I were to take the terms that I have here, right? I have 1/2, 1/4, 1/6, 1/8, 1/10, 1/12 still, right? If I were to kind of take and add in back in the terms 1 plus, let's see, how did they add equations 6 and 7? Oh, I see. So if we take our two equations we have here, actually, right? So I wrote these two down. This is true and this is true. If I add these together, right, I'm going to end up getting, I get 1 plus 1/3, right? And I have minus 1/4 minus 1/4, which is minus 1/2. And then I'd have 1/5. And then the 1/6 and the 1/6 cancels out. Minus 1/8 and minus 1/8 will still give me a minus 1/4. Right? So what's going to happen is adding these two series together, I still get the same sum here. It's still all the same terms. However, in that case, I'm getting natural log of 2 plus 1/2 natural log of 2. So I get 3/2 natural log of 2 instead, which is sort of funny because I'm adding all the same terms, I just changed the order, right? So that is why it matters to be conditionally convergent, because an absolutely convergent series will always have the same sum no matter what. A conditionally convergent series converges to a sum, but depending on the order you put the terms in, it may be a different sum each time. Like here, you can either get natural log of 2 or 3/2 natural log of 2, depending on how you order your terms, right? And we just solved that by taking our example here, right? You could do this. This happens with all convergent sums, right? That it converges, but it depends on how the terms. But if it's absolutely convergent, it doesn't matter how you add them. It's always the same thing. So it's nice to have that consistency in some cases to kind of study what happens. Okay, and that's it for the section. So any other questions for you at the moment? Yeah, that's just an interesting thought. I'm not going to ask you to find 3 different sums of this of the convergent series by rearranging the values. So okay, cool. Go ahead and take a break. We'll come back at 4:50. give you a little over 10 minutes, but I'm spoiling you guys. Wow, look at that. And we'll come back and we'll do 11.7.